Hi, this video is about charging by conduction. Some materials are good at conducting electricity through them. In other words, electrons can move around with relatively little obstruction. It's pretty easy for electrons to just pass through or get conducted like a train through these materials. Others are poor conductors, which we sometimes call insulators, and in these materials, excess electrons have difficulty moving and often they get stuck. I think a great illustration of the difference between a conductor and an insulator are plastic chairs versus metal chairs. On a plastic chair, I don't know if you've ever experienced this, but I feel like in my high school we had a lot of these plastic chairs that if you were to sit down on them, you would often get staticky and you would get shocked if you touched anything metal. And that's because plastic is an insulator, and if there are ever excess electrons or excess charges and they get deposited on the chair, they remain on the seat and they cause the charges to build up in one spot. And often it would seem like it happened on the back of the chair. And these excess electrons would just build up there if you rubbed up against the chair, and you would ultimately get shocked by these electrons. They wouldn't have anywhere else to go because plastic is an insulator. And so once electrons are put on the chair, they can't go anywhere else. They just stay there. Maybe eventually they jump into the air, but for a time being, they just kind of stick there on the chair. Now, a metal chair, on the other hand, is a conductor. And if you have excess electrons deposited on one part of the metal chair, then because metal allows electrons to move freely, the electrons can spread out on the chair and eventually find places to go, like the ground, for example. And so they don't actually stay in one place, but instead they freely move around. And it's interesting to note, like, they spread out because if you think about it, electrons are all negatively charged, and negative charges want to repel each other. They try to spread out in a conductor. And this is a rule actually in physics that excess charges always repel each other, forcing themselves to the outermost surfaces of any conductor. They cannot move to the center. And so this is why cars are safe in lightning storms, because a lightning bolt, let's say, deposits a bunch of excess electrons onto the car. Well, these electrons, because they're all negatively charged, they repel each other, and so they spread out on the car's surface, the outer surface. And they don't go into the center of the car, which is where the people are. So you're safe from lightning in a car because all of those electric charges always spread around you rather than going through the center of the car. So I want to show you a device that you can deposit charges on. It's called an electroscope. And I have a picture of it here, but I have the actual thing right here. Okay, now there's different versions of this, but this one basically it's got a long piece of metal here, a conductor, that's connected to these two hanging pieces of foil. And this is just like aluminum foil, for example. I'm not sure if this is aluminum or something else, but it's metal foil, and you can see it kind of just swinging back and forth there, two pieces. And it's two pieces because it shows us what happens when we charge these objects. So I'm going to take my classic balloon here, rub it up against my hair. What do you think will happen if I deposit these electrons that are now on the balloon? I can even hear them. It's a little staticky. There's electrons now on the balloon from my hair. If I take this and touch it to the metal, then the electrons will want to jump off and get away from each other and jump onto the metal. Now, if that's true, and this metal is a conductor, those electrons won't want to stay up here at the top, but they will want to spread out all along the outer surface of this conductor. And if they do that, they'll even spread to these little leaves of the electroscope, and the electroscope will acquire a negative charge. So I'm trying to draw that here. And if these two leaves both have negative charges, then they will want to repel each other. And they're free to move, they're just hanging there, so they can repel each other. And we should see these leaves spread. They should repel. So let's see if that happens. Sometimes this works, sometimes it doesn't. So look at the leaves here in the middle of this electroscope, and then I'm going to deposit some electrons on top. Watch the leaves. Wow, did you hear the shock too? I don't know if you could hear it, but you could hear the electrons jumping onto this electroscope. I've got a lot of electrons in my hair. Okay, watch it again. Oh, it jumped so far that it actually fell off. I don't know if you can, yeah, you can see that right there. That's never happened to me before. Oh, my hair is wild now. So we have a name for this in physics. The act of charging an object by touching it with another charged object, causing a transfer of excess charges, is called conduction. So like conductor, conduction. So let's look at a couple of examples of this. So I have a negative and a positive example. We just witnessed the negative example. So let's say you have a negative insulator, like a balloon or a plastic rod, and you bring it next to a neutral conductor. So like a metal sphere, like we just saw there. And if you touch that plastic rod with the metal sphere, all of these negative charges, these excess electrons, will want to repel each other and jump onto this metal sphere. Now the ones in the back are still stuck there because it's an insulator, they can't move. But the ones that are, touching or close to touching the conductor will, have enough ability to jump onto the conductor and spread out. And once they hit the conductor, they all spread around the outer surface. So now the conductor was neutral, now it's negative, and they're all spread out around. The insulator is still negative too because it's still got some negative charges stuck there. So this is what happens to charge something negatively. What if we brought a positive insulator next to this neutral conductor and touched it to the conductor? Well, positive charges can't move. They're protons. They're kind of fixed to the structure of the object. They're not able to move freely like electrons can. So will there be a transfer of charges here? And the answer is yes, but it's not actually pictured well right now. What we're not picturing here is that a neutral conductor, while it looks like it doesn't have any charges, it actually has lots and lots of charges. It's just that they all balance out to give a neutral net charge. So I'm going to redraw this so that it has a more accurate representation of the charges present in the conductor. So I'll be right back. All right, so I've drawn the positive and negative charges here, and you'll notice I tried to draw the positive and negatives together to show that these are atoms and they balance each other out normally and makes it a net neutral conductor. Now, if you bring this positive rod over here and touch it, it's going to attract some electrons. And since electrons are free to move in a conductor, those electrons are going to jump onto this positive rod. And I've tried to show that in the process of happening here. These electrons have left their positive charges behind. They're going to jump over to this extra positive charge over here that they're attracted to. And so you take the rod away, and what you have ending up here is, overall, it's still a positively charged rod. It's a net positive insulator still. But all of those electrons have been stolen, and we have a positive conductor over here. So you're still making a positive charged object here by conduction. It's just, it happens a little bit differently because the positive charges don't move, just the negative charges move. So that's all I've got for you in this video. Remember, shortcuts make long delays.